General comments about your superhero papers. Overall, I loved them. Of course, that's why I chose this assignment. It's fun. Many of you, I want to compliment. You got into the spirit of it. I could tell many of you put a lot of thought into it, whether you wrote it the weekend before or not. That I can't tell, but I can at least tell by reading it. Those of you that put a lot of thought of it and followed the instructions. On that note, many of you didn't follow the instructions, which were there the whole time. There were many things people forgot to do. Most people, remind you again, it was out of 30 points. So that number is out of 30. And then I translate that into the percentage out of 100. It's posted on WebAssign now. Most people got A's. There was a lot of good creativity. The most common threads, of course, were Newton's laws and the laws of thermodynamics by far, which was fine because that's what I expected. That's mostly what we covered in class. I think the most common superpower was something of the vein, absorbing energy, generally from the sun, taking it in and being able to shoot out heat or fire or whatnot, melt people in some fashion or another. A few people did a twist on it and made it the reverse, the cold instead. That was fun. And a lot of Newton's laws were the rebounding, They like to violate Newton's laws more than you guys abided them, which was fine. That was allowed. And so they would bulletproof, or people would run into them and just bounce off, or they couldn't get damaged one fashion or another. A lot of good creativity, a lot of good storytelling. I appreciated that. I tried to write comments on everybody's. I'm happy to discuss these afterwards, of course. And if you don't see why I'm justified in my answer, but score. Any questions at the moment on them? Yeah, that was in the instructions, one of the bullet items. The sources, if you didn't include your sources, it wasn't a major factor in my mind, like a point or two. I didn't take off much, especially if it was well written, and I could tell that a lot of people that forgot to include a works cited and cite their sources. That sounded redundant. I mean, technically that's plagiarism, but I could tell they had went somewhere, they had gained some knowledge, they just didn't note it. And so I realized you were researching. You probably just either didn't realize it, didn't review the instructions again, or never realized in the first place that you were supposed to cite, have a bibliography. So it wasn't a major factor, if that was all you left off. What's that again? What's the total out of? Tell them, class. 30, yes. I don't know if it makes you feel any better, but I don't think anybody got below a C. Anybody that turned it in had enough there, and I could tell they put enough effort in that they at least warranted a C, definitely. Everybody that turned one in. There's several that didn't. Go figure, but anyway. Okay. Another thing on way of transitioning into review. A student brought this to my attention. I'm not going to go into extreme detail, but you might find it creative. It's an article online that claimed, the title's, "Physicist Uses Math to Beat Traffic Ticket." Who's seen this? Quite a few of you. I can't tell you whether it's true or not, whether this actually happened. Basically, the gist is, he's moving along in a car, and he's coming up to a stop sign. There, how's that? And there's a cop over here. And so, as he's moving along, he's got motion. He does a paper. He wrote a paper on this, and that's what I think is funny about it. They took him to court, and he's trying to justify his way out of this ticket. The cop claims that he did not come to a full stop at the stop sign before he continued on. And so he argues, well, if I'm going at a constant velocity, which means what? No acceleration. Same direction, yeah, and we're not speeding up or slowing down. Good, very good. And it went along. This person, as something comes by, actually looks like they speed up and then slow back down. We didn't get into circular motion, which he goes into, but the gist is, if I'm standing here and something's approaching from over there and it comes this way and then goes that way, as it passes by me, it seems like it speeds up. Just think of it this way. Far away, it doesn't look like he's moving much. But as he gets closer and closer and closer, relative to you here, he kind of whips by you, and it seems like he sped up right then, and then slows back down. So one part of his argument was that, the cop didn't realize that. He was measuring angular velocity, velocity in a circle, rotation, as opposed to linear velocity, what we studied in a straight line. Well, then he says, but in reality, I did stop, so I was decelerating. What's that mean? Slowing down, yep. If this car is moving that way, which direction is his acceleration as he approaches the stop sign? Point. Good, that way. Yeah, he can, remember, as a review, you can still move that way, have motion in that direction, but you can be slowing down, which means you're accelerating that way. Which way is the force being applied? Point. That way. If you're accelerating, remember Newton's second law? In order to make a mass accelerate, there must be a force applied. So yeah, the brakes apply that force to decelerate him that way. So he slows down, stops, and then he claims, of course, he immediately sped on up and accelerated back. And he works out this equation that if any of you look it up, don't worry about. But what I found interesting is that his physics was wrong. He figured out if I'm moving, if it takes that distance to slow down, he used a formula we saw once, way back now, that 1/2 times the acceleration times the time squared. So in other words, if his acceleration is 10 meters per second squared, and this takes him, 2 seconds to come to the stop, how far would he move? So you'd put in 10 here. The 2 seconds, so what's that? Half of 10 is 5, 2 squared is 4, so 20. So it would take 20 meters to do that, and he was trying to show this to the cop. But it's just fun because he's actually trying to apply physics. Whether this is true or not, again, I don't know, but he got off. He did not have to pay the ticket. At least if the judge was baffled. And after me studying the physics, I think he was hoodwinked. Because there's something wrong with this. This is the formula he based his graphs on. This car is already moving. We have to look at inertia. He already has a velocity. If he's going to slow down, that means he's slowing down from something already. So if you're just moving without acceleration, distance is velocity times time. Do you remember that? If you're going 100 miles an hour for 1 hour, how far do you move? 100 miles. 100 miles an hour for 1 hour, you move 100 miles. Well, so the fact that he's already moving over a certain amount of time means he's going to travel a certain distance just from his inertia, keeping him going. And he'll travel yay far from decelerating as well. So in reality, this distance should add together. He should have accounted for this and for this. Anyway, I can give you the link, or you can look it up. Physicist uses math to beat traffic ticket. But somebody was trying to have fun anyway. Now, I thought how I should approach this review. And we got many methods. Go over homework. I can just sit here flipping through my pages. We can answer your questions. All of the above. I was leaning towards, I mentioned once before, when I wrote your guys' homework and exams, each in turn, I took made up questions and looked at a bank of questions and said, I like this one for homework. Oh, I like this one for the test. I don't like that one. Oh, this would be good for the final. And I stuck it in a Just kind of moved it over there. Here's all the questions I did that for, thinking, oh, these would be good for the final from everything. So if I walk through them, it'll review some concepts, and maybe you'll get lucky and I'll ask the exact same question. But if you guys have questions, please bring them up. It's better than me just shooting off the hip. If there's things you're confused about, let's hone in. Also, this is your time to make sure you understand the answers and my solutions to all those homework and exams. If you've never looked at them, which I know a lot of you haven't because I can see, then if you don't know why it's the right answer, you're probably going to miss it again. I'd hate for that to happen. Excuse me. We won't have a method for making up or retaking the final. I posted it as an announcement. The final is next Wednesday, not Wednesday, but in a week after Wednesday, on the 2nd, in here at 10:30. They put out 2 hours for it, 10:30 to 12:30. It's going to be the same format. I'm not going to switch it up on you now. Multiple choice type. There will be more than 30 questions, but right now I don't intend on doubling that because, why? So most of you should be able to get done in plenty of time, but you'll have 2 hours to work on it. Questions about the final format, time, logistics? Burning questions right now that you thought about on the weekend?
This isn't necessarily a business question, but will we know our school, so like the retake test is open until tomorrow. Are we going to know what we want on the test before that retake is closed?
No. You will not know how you did or which ones you missed on exam 4 before you turn in the retake. The retake is due tomorrow, 11:59 p.m., so that we can discuss it Wednesday if need be. But you'll have a week then to see the solutions, because they'll pop up as soon as the due date comes up. Remind you again, if you choose to retake it, you don't have to, but if you choose to retake it, I'm going to average the 2 scores. Because it's open book and most people do better. But yes, there is a chance you could miss all of them. I will average that. So if you don't want to retake it, don't submit anything. Yes, you had a question. Well, yeah, then I'll average that in. I'll average the 2 grades. I'll be blunt. Shame on you if you do worse. You can talk to friends. You have the book. You have my lectures. You have the notes. I figured you could look up the answers. Learn what you weren't sure of test day. And hopefully at least do somewhat better. If you do equal or better, it'll improve your grade. You'd have to miss more, than you missed test day. And my guess, if anybody puts forth any effort, which is my point, to have you put forth effort, hopefully you're learning in this, giving you a chance to improve your grade. But you don't have to take that chance if you're worried. You can just go with normal test. Day grade. I expect to get your results this afternoon. They email me them as soon as they finish sending them through their machine in the testing center, which they don't run over the weekend. You can, if you want, you can email me this afternoon or something. If I have your grade, I can tell you your final grade that you got on test day. If you just, I gotta know. If I have it, I'll tell you. All right, I'm gonna go down through these. Then picked out some of them. We won't have time to go through all of them. I'm not gonna ask you all these. I'll have to whittle it down. But it'll be that way. It'll be a good review. A sheet of paper can be withdrawn from under a container of milk without toppling it if the paper is jerked quickly. So I'm pulling the paper out from underneath a bottle of milk. What is that demonstrating? What concepts? Inertia. Good. Inertia is defined as resistance to change. Yeah, change in motion. Which Newton's law is this associated with? The first law, things at rest want to stay at rest, and things in motion want to stay in motion. Most of you have a real good grasp on that now. That's great. So the idea is you pull something out underneath it. It's at rest. It wants to resist being moved. This is trying to move it as you pull it along. So if you can do that quickly, that force isn't applied for as very long, and its inertia keeps it in place. Good. Yeah, I like this one. A man weighing 800 newtons stands at rest on 2 bathroom scales, so like one leg on each, so that his weight is distributed evenly over both scales. The reading on each scale is what? So he's 800 newtons standing on 2 scales. What will the individual scales read? 400. Good. So he's got a force down of 800 newtons. Newton's third, well, he's balanced. He's not moving up, he's not moving down. So the net force on him is 0. The net force on him. In other words, the combination of all forces on him. Well, if that's the only force, he should be moving down, accelerating down. He's not, so there must be forces pushing him up. And it's the forces of the scales. They must total 800 newtons to balance him. So if he's evenly distributed, then each one's pushing up with 400. What if he leans to this side? Yeah, 800. 800. Somewhere in between. But yeah, if you're even, 400. While an object near the Earth's surface is in free fall, its what? Velocity increases, acceleration increases, mass increases, or does its mass decrease? What's changing while an object near the Earth's surface is in free fall? What's increasing? Raise your hand if you think it's acceleration. Velocity? Mass. No takers on mass. Well, that's good. Why acceleration? Because it's squared? Falling at a rate squared. You remember those pictures when something falls. That at first it doesn't, say the first second it doesn't seem to fall very far, but then the next second it falls even farther, and the next second even farther. Yeah, there's a squared factor there. That doesn't justify to me yet whether that means acceleration increases or decreases. Somebody, yeah, go ahead. Bless you. The acceleration near the Earth, we call the acceleration due to gravity. We use little g, and it is it equals negative 9.8 meters per second squared, about 10 meters per second squared. That's a constant. So through this whole fall, it's always being accelerated at the same rate. The Earth's mass and the object's mass are attracting each other. There's a force between them, and that force isn't changing, neither is the acceleration. That's what gets it to fall. So if its acceleration is not increasing, what is? Velocity. Because acceleration is a change in velocity with time. It's the rate at which you're changing your velocity. And that can happen 3 ways I can think of. How can you accelerate by changing velocity? One way? Change direction. Good. Because velocity is a vector, and if you're going in a circle, there must be an acceleration there. There must be a force causing you to go in a circle and accelerate. You're not changing your speed, or you don't have to, but you're changing your direction, so that your velocity still changes. Well, since you got to the crux, I want to make sure people realize the other two are easier. You speed up or you slow down. There are other ways to change your velocity. So, when I throw this piece of chalk up in the air, what's its acceleration now? On its way up, what's its acceleration? How come you guys don't all sound confident? Honestly, if you don't get, if I'm saying something in the review and you don't get it, now's the time to stop me. Yeah, it's still this. It's always this. Whether it's moving up, right at the very top when it stops. Remember, it cannot be moving right at the top and still be accelerating. Because it's changing its direction. It goes up. There's still a force being acted on it, causing it to accelerate down the whole time. Slows down, stops, still being applied, so it speeds back up. Its velocity is changing, of course, but its acceleration does not. The other weird concept most people, see, this sparks my head too to talk about things. Inertia. Most of you got this because you did great in your superhero papers. Why do things slow down on Earth then when we just throw them or roll them or our car? Air resistance, friction, yeah. So Newton's laws are still valid. They say things will stay in motion if no force is applied to it. We just forget about those forces that we're so used to. So out in space, you throw something, it'll just keep going. Which led to one of the bigger confusions. If you had an elevator and it's going up, it's in its motion going up. Let's say it's going at a constant velocity. V is, I don't know, 5 meters per second up. It's moving up. Is it accelerating? What's its net force? Zero or non-zero?
If it's not accelerating, it's zero.
Yeah, this is a confusion. It's moving, so people go, oh, in order to be pulled up, there must be a force. You're right, there must be a force pulling it up, but it has its weight pulling down. And we'll draw them equal magnitudes. If this balances that, then the net force is zero. Do you agree? If the net force is zero, there's no acceleration. And if there's no acceleration, the velocity is not changing. So this can still be going up with no net force, no acceleration. Don't get confused. There's still a force pulling it up. It wouldn't move up if this wasn't pulling. It would fall down. But once things are moving, it doesn't mean they have to be accelerating. Now, I think I remember it was Innes was observant back then. To get this thing moving in the first place, initially it's not moving. If you applied them equal, it wouldn't change its velocity, would it? If these are equal, there's no net force, there's no acceleration, that's not changing, nothing would happen. So initially, this has to be a little bigger. Now there's a net force, a little acceleration, and we can change this and get it up to something. Once it gets there, though, it does not need to maintain that. It can balance, and its inertia stays at 5 meters per second. If it remained larger, what would happen? Yeah, it would go up faster and faster and faster and faster. And we don't need that. We don't want that. We don't like how that feels. Well, at amusement park rides, but not in an elevator. Do you remember we had the two people on the carts down here? I called them push me, pull me carts for Newton's third law. And we had them push off each other. and we had a larger person, and a smaller person, well, how does the force compare on the two? Who pushes with more force? Oh, bless you. You got it after a semester. Yeah, they're the same force. Sure, the big guy probably has the potential to push harder than the smaller guy, but he can't push any harder than the smaller guy can push. You say the smaller guy is at his breaking point, what's he going to do? Give, which means this guy can't push on him as hard. So the force between their hands, the force on him and the force back on him, are going to exactly the same magnitude. Now the one everybody still likes to miss, though, is Mr. Mosquito. Bzzz. Now let's do a glow bug. Firefly, they're fun. At night in Kansas, and you're traveling along, and wham, it hits your windshield right when he's glowing and makes a nice fluorescent streak, and I looked at it all the way home. But who feels more force? The windshield or the bug? They are the same. Do you believe this now? So why didn't the windshield break? Yeah, it can handle that much force. The bug couldn't. Same force, bug couldn't handle it, yeah. Who was affected more? The bug. And that had to do with the mass, Newton's second law. For that same force, the small mass, the little bug, got accelerated too much, more than he could handle. And vice versa to the windshield. Newton's third law came up a lot this semester. The tug of war, I know a lot of people you didn't like. Strong man pulling on a rope, and little Susie over here pulling back on the rope. And most of the time in tug of war, they're kind of at a standstill. But it's a lot like this. Even if, we know who's going to win, right? The strong man. He's pulling this way. So initially, he can exert more force, and it's a little bigger, and then the whole system starts moving this way. That's why the strong man wins. But he does not have to keep pulling with more force. All he has to do is pull with the same force she's trying to pull back. And they can just coast along at a constant velocity real slowly until the flag gets over the middle point and he wins. Because whatever force he pulls, that's what she's pulling back, if they're at least trying to pull. It's Newton's third law. The tension in the rope just allows that force to be translated over to her. Where else did we see Newton's third law? Charges. Are they attracted or repelled? Attracted. Why? Because they're opposite, yes. Anything more? There's an electric field. Goes which direction from him? Yeah, away. And so towards this guy. And we're going to get like this. Whee! Okay. All right. This guy has an electric field. If you put this charge feels that electric field, and what happens? Physics terms is what I'm looking for. Yeah, give me anything. What's going to happen to him? What, Michael? A little louder. No, that's if they touch and transfer charge. But you got a positive charge here, a field. This guy's in that field. So he feels a attraction, force. The reason they're attracted is, yeah, there's an electric field, by definition opposite to attract, but it's because he feels that field. Let's see, what was it? Electric field is a force per charge. And so he's going to feel a force. Remember, you need a force to make something move. Change his velocity. If he's not moving, his velocity is 0. We need to accelerate him this way. And he's going to get pulled that way. Because there's a force acting on him. It's caused by this guy's electric field. Well, this guy has his own electric field. And he feels the negative charge's electric field. So what happens to him? He feels a force in that direction. That's why they're attracted. This one feels a force to the left, and this one feels a force to the right. He attracts him, and he attracts him, or her. And how do those forces compare? Thank you. They're equal. We saw it with what was it? Some constant. The two charges. If you plug in values, whatever plus charge and whatever negative charge, do you see that they both contribute to the force? That's the force each one independently feels. Charge 2 feels a force on it from charge 1. That force. Charge 1 feels the same force from charge 2. They're equal and opposite. Newton's third law shows up. And what happens with magnetism relating to this? Can anybody make the extension? Yeah, it's the same thing. Instead of using charges, there's a different constant. And it's the pole strength, the magnetic poles, north and south, or south and north and north. But, so if I have a bar magnet here and a bar magnet there, the force this one exerts on this one is the same this one exerts on this one. They have to be the same. Yeah, let's make it easy. One you can relate to: Earth, big mass; us, puny mass. This, and that works with this too. Same inverse square law with gravitational attraction. So I expect the forces to be the same. So if I'm being pulled to the Earth with 170 pounds of force, remember, that means I must be attracting the Earth to me with 170 pounds of force. Yes, absolutely. We're attracted to each other. We come together. Why don't we ever see much of an effect? Because this is huge! And back to Newton's second law. If we feel the same force, then really big M, little effect. We don't see much. Where little m, we see a big effect. But yes, don't be swayed because this is so much bigger. Like the Mack truck's windshield and the little firefly. Newton's third law says equal and opposite pair reaction forces. What's terminal velocity mean?
It's that you're falling at a constant rate, so you're no longer accelerating.
Excellent. You're falling at a constant rate, constant velocity, which means you're no longer accelerating. That would occur when?
When the force from air.
Yeah, air resistance. Drag, right. The air, your weight's being pulled down. That's why you accelerate. But if there's an equal force up on you caused by air drag, then they're balanced. The net force is 0. There's no acceleration, net acceleration. So your velocity will no longer change, and you'll stay going at whatever speed you were at because of your inertia. That's terminal velocity. And that would happen to us if we fell out of an airplane. At some point, we wouldn't fall any faster. It's too fast, but Which is why a lot of bugs, insects, or even some animals can land on the ground safely from falls from really high heights. They reach terminal velocity, which isn't too fast to kill them. It's too fast for us. Our terminal velocity is still too high. You can increase the air resistance by spreading out more surface area. There was a great paper concept where they increased the area of the person. Actually, there were several. Some people did it, you did it differently too. Some grew flaps. Squirrel Boy, I remember. Another one was Poor Man. His pores would expand and increase his surface area. which can contribute to the amount of lift and air resistance. So that was fun. Okay, compared to a 1 kilogram block of solid iron, a 2 kilogram block of solid iron has twice as much what? Inertia, mass, volume, density, what do you think? So we got a 1 kilogram block of solid iron and a 2 kilogram block of solid iron. Tell me what you know. Think about inertia, mass, volume, density. What about mass? It's double. Yeah, if it's 2 kilograms, kilogram is a unit of mass. Right? There's twice as much of it, so the mass is doubled. What else did you know? Yeah, you doubled the mass, you double the inertia. Very good. You increase density? Oh, we're getting some no's. It's still iron. And iron is iron. So it still has the same density. Do you remember what density is? Density was the ratio of mass to volume. And since it's still iron, we didn't change the density. If that doesn't change, it's still iron, and we doubled the mass, what had to happen to the volume? Yeah, to have 2 kilograms of solid iron compared to 1 kilogram, it'll take up twice as much space. So the mass doubles, which means the inertia doubles, which meant the volume doubled. But the density didn't. It's still iron. Which one would sink and which one would float? Thanks. They'd both sink because their density is greater than water, much greater than water. If you put it in mercury, yeah, it would float, that's for sure. All right. A bag of groceries has a mass of 10 kilograms. What's its weight? Can you solve that? 10 kilogram bag of groceries. 98 newtons. Excellent. It's this formula again. What did I just say? 10 kilograms? Yeah, that's the mass. To differentiate, there's a difference between mass and weight. They're not the same thing. A lot of you got confused at the beginning. We've had time to mull it over. A kilogram is the mass. And it's being accelerated downward at 9.8 meters per second, or 10, all round. And so its force is 100 kilogram meters per second squared, which is the same thing as a newton. Newton is a force. Your weight is a force, the force you're being pulled down at. So a 10 kilogram bag of groceries is 100 newtons. That's what its weight is. In order to lift it and hold it right here, how much force would you have to apply? It's slightly greater to get it moving, but then just to hold it there, all you need is 100. Yeah, and if I move it at a constant velocity, I'm still only applying 100. Just sparking any questions? And oh, right, I forgot about that. Okay, so is it sailing well? I'm fine with 10. It'll make math easier. If it matters, I'll tell you. And generally, you can use either one because whatever answers I'll give you, 9.8 or 10 will get you, oh, this is the only one near it. The others are way too far away to be right. And if you're ever in question, just ask me and I'll tell you which one you can use. We did that. This is good. Good. I figured we'd spend more time on the first stuff because it's been longer. That was all of my questions for exam 1, and we've touched on some other stuff. We did that. Then we got into collisions. Oh yeah, momentum. Let's end with this one. A 5 kilogram shark swimming at a speed of 1 meter per second, swallows an absent-minded kilogram fish. Do you remember this stuff? Toward it at 4 meters per second. So we got a 5 kilogram shark swimming towards a 1 kilogram fish. That's how fast they're going, approaching each other. The shark swallows him. There's a collision. Is that an inelastic or an elastic collision? It is inelastic. You remember? Elastic is when they bounce off, kind of rebound, don't stick together. Inelastic is where they swallow, they combine, they're together, they stick. A lot of the kinetic energy is converted to heat or deformation of the crumpling up your car or something. That's inelastic. Elastic, they just kind of rebound, like billiard balls or something. So this is inelastic. What's going to be conserved? Do you remember the term? Momentum. Momentum. Momentum is mass times velocity, that relationship. And total momentum is always conserved. So the total momentum of our system, the fish and the shark, is what? Let's see. His guy's momentum is 5 units. Mass times velocity. His is 4. This way, and that one that way. So the total momentum is what? 1. That way. So what does the total momentum have to be after he swallows the fish? 1. That way. So if you write all this out, it'd be like mass 1, velocity 1, mass 2, velocity 2. That's what we just did. Initially, before the collision. Must equal that. Well, they're moving together. After the collision. We know that has to equal 1. To show you, this would be 5, this would be 1, this would be 1. What would this be? -4, because it's going the opposite direction. You could very well say to the left is negative, but then you have to make to the right positive. I went with convention and said to the right positive, so the left has to be negative. They have to be opposite. That's how you get the 1. So over here we're going to have 5 and 1 moving at something, and that's got to equal 1. So what's the velocity equal? 1/6. 6 divided over, and you get 1/6. So it'll be going 1/6 of a meter per second to the right after he swallows the fish. So collisions, we use that momentum conservation. Is that coming back? Groovy. We'll continue more next time.